So in the last video we saw how we could turn this low voltage alternating current into a low voltage, still alternating but entirely positive signal here at the output by using a diode in a half-wave rectifier. In this video we're going to look at how we can turn this still varying signal into something closer to the low voltage direct current constant voltage that we're looking for. Remember, if this is 12 volts over here and this is 0.7 volts forward bias voltage across this diode, we're going to have 11.3 volts left over at the output. Okay, remember there's always 0.7 volts lost across there. So let's look at this problem that we're faced with. We want to turn this alternating signal, or this varying signal here, into something that's constant. And how can we go about doing that? So to explain this a little bit more, let's imagine that we're on a farm. Instead of representing voltage, this graph represents rainfall. Here we've got lots of rainfall, and in these periods here we've got a bit of a drought. We don't have any rainfall at all. So what are we going to do? How are we going to solve this problem of maintaining our farm with a constant flow of water during the drought periods? Well, we'd use one of these, okay? We'd use a water tank, and we would store water from these bountiful rainy periods here to help us have water over the drought, okay? So somehow, in this circuit, we're going to need to store electricity, store electrons, store voltage, store current, store something, okay, to get us through these lean periods and create that constant voltage. So to explain how we're going to achieve this, let's look at this simple circuit. We have a battery, a switch, and a resistor. And that circuit is all connected up with bits of wire. All of those bits of wire are filled with electrons. So there are the electrons there, spread evenly around the wire. Obviously there are billions and billions and billions of them, but instead of billions and billions, I'm using 10. And but this isn't a negatively charged wire. If we just had these electrons around here, we just have a negatively charged wire. Of course, the wire is neutral, so it's also got protons, and each of those electrons is balanced out by a proton with positive charge. And there are the protons represented by those positive symbols there. So what happens in this circuit when we close the switch? Well, let's just consider we've got positive side of the battery, negative side of the battery. Conventional current will flow from positive to negative, and therefore electron current must flow in this direction. So let's just see if we can see that in action. Close the switch, close this break in the circuit so there's a path for electrons to flow, and okay. Did you spot the deliberate mistake with that last video? I'm not going to film it again because it took ages, but problem was the electrons were actually flowing in the wrong direction. So they're supposed to flow from negative to positive, and I had them flowing from positive to negative. Don't make that mistake. And what we've just seen here with the open circuit is essentially how a capacitor works. A capacitor is a tiny break in the circuit between two metal plates. And when a capacitor is working, electrons build up on one side, positive charge is left on the other side, and we create a voltage between these plates. Then, if we take away this electromotive force here, okay, the force that was pushing the electrons on here, the Coulomb force repelling the electrons from each other pushes them back and causes a current to flow again in the circuit, even in the absence of this voltage. And that will achieve what we're trying to achieve. We're trying to achieve that constant flow. Let's look at it in even